Welcome to a new video in the series Graph, Homomorphisms and Universal Algebra. In a previous video we have learned about the connection between primitive positive definability and preservation under polymorphisms. This link between logic on the one hand side and algebra on the other hand side is of fundamental importance to this course. In a later video we have learned about primitive positive interpretations. The big difference between definitions and interpretations is that a definition works on a fixed domain, a fixed universe, whereas interpretations can be used to relate structures with different domains. Quite fascinatingly, the connection between logic and algebra continues to interpretations. Whether or not a structure A primitively positively interprets a structure B can be characterized purely algebraically. And the concepts that are involved in this characterization are of fundamental importance in universal algebra. So today we'll look at the fundamental concepts of a subalgebra, a homomorphism, and products of algebras. In the second part of the video, I will present the logic-algebra connection. An algebra in universal algebra is simply a structure where the signature only contains function symbols, no relation symbols. We still use the convention that the domain and the algebra are typically denoted by the same letter, but the algebra is underlined. A group, for example, is a structure whose signature contains a binary multiplication operation, a unary operation for taking inverses, and an operation of arity 0, that is a constant, for the neutral element in the group. Other examples are rings, fields, modules, semi-lattices, lattices, Boolean algebras, and many more. Let A and B be algebras with the same signature tau. Then we say that B is a subalgebra of A if, first of all, B is a subset of A. For relational structures, there was no restriction on the choice of the subset B. For algebras, this is different. There is an important restriction that we have to impose on the set B. Let's have a look at an example of an algebra with a single unary operation F, which can be nicely drawn. The red subset of A in my picture is not a good candidate for a subalgebra of B, because B should become an algebra, where the function symbol F denotes an operation that is defined everywhere and does not map elements to elements outside the set B. The blue set, on the other hand, is closed under applications of F. So we can define an algebra on the blue set such that the function F on this set B acts in the same way as the function f of A acts on the blue set. And this becomes our official definition. We want that the domain of B is closed under applications of operations of A to elements of B. And we want that the functions of A coincide with the respective functions of B on the set B. If you think about this for a while, what it means, for instance, for groups, then you will see that a subalgebra of a group in the signature that we have chosen is nothing but a subgroup. Similarly, this definition captures the definition of a subfield and so on. If F is an arbitrary subset of A, it might not be the domain of a subalgebra of A, but there is always a smallest subalgebra of A that contains S, which is called the subalgebra of A generated by S. In our example, the blue set is the domain of the subalgebra of A generated by the red set. We now define homomorphisms for general algebras. Again, the definition is as expected. Most of you already know it from the special case of groups, rings, and so on. Let A and B be algebras with the same signature tau. Then a homomorphism from A to B is a map H from the domain of A to the domain of B, such that for every function symbol F in the signature, say of arity K, and for all elements A1 up to AK of A, the following holds. Instead of first applying f to a1 up to ak and then applying h, we can also first apply h to each of a1 up to ak and then apply f to the resulting k-tuple, and we will get the same value. On the right, I draw an example of a homomorphism from the easy situation where tau has a single unary function symbol. Here are some general useful observations about homomorphisms. The first is that the image of a homomorphism is always a subalgebra of B, which is called the homomorphic image of A under H. The kernel of H, which is the binary relation that contains all those pairs of elements that are mapped to the same element of B, is a so-called congruence of A. A congruence of an algebra is an equivalence relation which is preserved by all the operations of that algebra. In our picture, we have a congruence with two congruence classes. Conversely, every congruence of an algebra gives rise to a certain homomorphic image, which is defined on the congruence classes, such that the map that sends an element of A to its congruence class is a homomorphism. Again, this is well visible in our picture. To define products, let A and B again be algebras with the same signature tau. Then the product algebra, A times B, is the algebra with signature tau whose domain is the set of all pairs whose first entry is from A and whose second entry is from B, and whose operations are defined component-wise. That is, if we apply an operation of the product algebra A times B to a set of pairs, we apply the corresponding operation of A to the first entries of the pairs and the corresponding operation of B to the second entries of the pairs. And the resulting pair is the function value of the operation. Infinite products are defined similarly. A power of an algebra A is a product of A with itself. I will now explain how algebras arise naturally in this course. But first of all, we will observe that every algebra gives rise to a clone, the clone of all term operations. Let A be an algebra with signature tau. By a term, I mean an expression that is recursively defined by the symbols in tau and by variables in the usual way. So let's have a look at an example. If tau is the signature of groups, then the following expression that I've drawn on the right is not well formed. But the expression x composed with the inverse of y composed with z is a valid example of a term. If x1 up to xk is some fixed set of variables, and t is a term formed with variables from x1 up to xk only, then t defines a function from a to the k to a, namely the function that maps a1 up to ak to the element obtained from the term by evaluating it in the algebra A after replacing x1 by a1, x2 by a2, and so on. If A is a group, then the term function for our example term above would be an operation satisfying the Maltsev identities that we have seen in an earlier video. In this case, we also call T a Maltsev term. It is easy to see that the set of all term operations of an algebra A is closed under composition. It also contains the projections. For example, if k equals 2, then the term that just consists of the variable x1 is the binary projection to the first argument. So indeed, the set of all term operations over a given algebra forms a clone, which we denote by clo of that algebra. Many properties of an algebra A only depend on the clone of term operations of A. For example, whether or not a certain set is a subalgebra of A only depends on clo of A. Also, the question whether a certain relation is a congruence of A only depends on clo of A. We have just seen how every algebra gives rise to a clone. Conversely, every clone can be turned into an algebra as follows. For every operation in the clone, we introduce a function symbol that precisely denotes this operation. Of course, we have to fix a signature to do this. So the algebra that we obtain is not unique, but usually the choice of the signature is not important. In particular, we can view polymorphism clones as algebras. In this way, we can translate back and forth between logic terminology and algebraic terminology. This translation is particularly easy if the domain is finite. So we will assume in the following that the domain is finite. If you have a structure A and turn its polymorphism clone pol of A into an algebra, and this algebra has a subalgebra B, then what does this tell us about the structure A? Well, B is preserved by all polymorphisms. So by what we have learned in previous videos, the set B is primitively positively definable in A. Conversely, if a subset B of A is primitively positively definable in A, then B is preserved by all polymorphisms of A, and hence B is a subalgebra of pol of A. Similarly, a binary relation C on the domain of A is a congruence of pol of A, if and only if C is an equivalence relation and primitively positively definable in A. In general, a K-array relation over A is primitively positively definable in A if and only if it is the domain of a subalgebra of pol of A to the K, the kth power of the polymorphism algebra. All these observations are straightforward consequences of the theorems that we have learned about polymorphisms in the video about clones. Suppose that we have a class of tau algebras K. Our classes are usually closed under isomorphisms, so I don't write set of tau algebras, but class of tau algebras, to avoid set theoretic problems. If you don't understand what I mean here, don't worry. We now define some operators on classes, which take a class and return a larger class. P of K is the class of all products of algebras in K. In particular, we allow infinite products. So even if K only contains finite algebras, P of K usually contains infinite algebras. If we don't want to allow infinite products, we write P fin of K. S of K is the class of all subalgebras of algebras in K. And finally, H of K is the class of all homomorphic images of algebras in K. When working with these operators, there are usually many brackets to write. So in order to save us some notational clutter, we write, for example, HS of K instead of H applied to S applied to K. And we write H of A for an algebra A instead of H applied to the class that just contains A. We now wonder what happens if we apply these operators over and over again. Do the resulting classes eventually stabilize, or can they keep growing and growing? A class of algebras with the same signature is called a variety if it is closed under H, S, and P. It is called a pseudo-variety if it is closed under H, S, and P fin. The variety generated by an algebra A is the smallest variety that contains A. We have a similar definition for pseudo-varieties. Note that the pseudo-variety generated by a finite algebra only contains finite algebras. And now comes a lemma. Let A be a finite algebra. Then the pseudo-variety generated by A is precisely HSP fin of A. And the variety generated by A is precisely HSP of A. So it suffices to apply each of the operators once, and in this specific order, to obtain the entire variety generated by A. In both statements, one inclusion is immediate from the definition. For the converse inclusion, it suffices to verify that HSP of A is indeed a variety, because the variety generated by A is the smallest such class. And the proof here involves some computation that you can find in the script. We have this logic algebra connection. Suppose you have a structure A and you have an algebra B in the pseudo-variety generated by the polymorphisms of A. What does this tell us about B on the logic side? Well, there is a finite power involved in the pseudo-variety. There is a homomorphic image and a subalgebra. This might ring a bell. In interpretations, primitive positive interpretations, we also had a finite power. We called it the dimension. We also had a primitive positive definable equivalence relation for the interpreting formula for equality. And we also had a subset which is primitively positively definable. We call this primitive positive definition the domain formula. And indeed, after the break, we will see how pseudo-varieties match with primitive positive interpretations. Here comes the connection between primitive positive interpretations and pseudo-varieties. Let A be a finite structure. Then a structure C has a primitive positive interpretation in A if and only if there exists an algebra B in the pseudo-variety generated by pol of A, such that every operation in B is a polymorphism of C. The idea of the proof is precisely to follow the strategy that I told you before the break. Taking a finite power, forming homomorphic images, forming subalgebras, precisely corresponds to what we can do with primitive positive interpretations. Note that, combined with the things that we have learned about primitive positive interpretations, this tells us that the computational complexity of the constraint satisfaction problem for A is fully determined by the pseudo-variety generated by pol of A. So we have taken another abstraction step. We might now wonder, what if we replace the pseudo-variety by the variety? We know that the variety generated by an algebra of size at least 2 contains infinite algebras, while the pseudo-variety of a finite algebra only contains finite algebras. However, in the theorem that we've just seen, in the proposition, we were only interested in the finite algebras in this class. So, can we replace HSP fin by HSP in this proposition? It turns out that the variety and the pseudo-variety generated by a finite algebra have precisely the same finite members. This is a consequence of Birkhoff's theorem. Birkhoff's theorem, which we'll prove next time, is a fundamental result in universal algebra. I have met famous mathematicians who said that as a student, Birkhoff's theorem was their most favorite theorem. This is probably not because it's terribly difficult to prove. We'll see a rather short proof next time. It's rather because of its elegance, I believe, and because of its usefulness. In any case, its proof contains some extremely important ideas.